We're going to look at one more example of the greedy method applied to solve the task scheduling problem. So this problem is defined as we have a set of tasks, we've got n tasks. Each task has a fixed start and an end time, so a given task has to begin at that start time and it must end at that end time. We don't get to shift it around and move it and start it at a different time. But our goal is we want to perform all of the tasks, and we have machines that can execute a task, but a machine can only execute one task at a time. It can't execute multiple tasks simultaneously. So once one task ends on that machine can now execute another task, but it can't schedule overlapping tasks. And the goal is we want to minimize the number of machines so that we still execute all tasks. Now this has other applications in resource allocation problems. So for example, with course scheduling, given the many classes that the computer science department will have, we want to figure out how we can schedule all of those classes so that we've got for each class a fixed start time and an end time, but we want to use the minimum number of rooms because it costs money to pay for the electricity and heating and so forth for a room. So we want to run all of those classes in the least number of rooms so that we don't have any two classes that are scheduled at the same room at the same time. Okay, so for example, if we were given the following tasks, it's possible that we could execute, so we've got here, this is the start time and the end time, and these are fixed. Again, we can't move them around and start them or end them at different times. We can execute all of these tasks using only 3 machines, and this is optimal. So for example, we've got the task starting at 3 and going to 7 here, and the task 1 to 3, this one, going, here. So this is an optimal solution. The question is, how do we come up with this optimal solution? We want to figure out the minimum number of machines we need to execute all tasks so that none of them overlap. Well, we can start by, given our set of tasks, we're going to keep track of how many machines, this is little m, how many machines we're using so far. So initially this is 0, and then we're going to increase as we see if we need more machines, we're going to add more machines as necessary. But we want to add the least number of machines. So we're going to go through every item in our set of tasks, each task that we have, and take whichever task has the smallest start time. So we could sort them in ascending order by start time first, grab whichever task has the earliest start time, and then check to see, is it possible that we could schedule this task already on one of the machines that we had made before? If it's possible, then we're just going to schedule this task on that same machine. So if we know that there's a machine, that won't conflict with the task that we need to execute, meaning that none of the other tasks on this machine conflict with this task. None of them are overlapping. So there's a free spot on this machine in between the start and the end time of our given task. Then if there's no conflict, then we're just going to schedule that task on one of the machines that we already have. That way we don't have to create another one. But if this task conflicts with all of the other machines that we have already, meaning that during that start and end time, on all of the other machines, we have some task which is already scheduled, which overlaps with that one, then that means we can't possibly use one of the machines we already have. We have to have another one. So in that case, if this task conflicts with all of the other machines that we've got, then we're going to schedule it on a new machine. We need a new machine to handle it, so we increase n as the number of machines we've got, and we're going to schedule this task on that machine. So before we get into the runtime here, because this will kind of depend how really are we checking if there's a machine that will fit this task and how we grab the task with the smallest start time. So a few details are hidden here, but I want to show first why this will guarantee that we get an optimal solution, meaning that we get a solution which schedules all tasks and uses the least number of machines in order to do so. And we're going to use another proof by correction. So we want to show that this will produce an optimal solution, that this has the greedy choice property. And in order to do that, we're going to assume that it doesn't, that it isn't an optimal solution, that instead there's some other, even better solution that our greedy method doesn't come up with. So let's suppose, by contradiction, that we have an even better schedule, one which uses less machines. Our greedy algorithm uses, let's say, k machines, and we've got an even better solution which uses less machines, which is better in that sense, uses less machines than what our greedy solution chose. So let's say we've got here machine 1, here machine 2, all the way up until here's machine k minus 1 and machine k. And on each of these machines, we have some tasks which are scheduled. Okay? So maybe here's a task scheduled. Just kind of visualize this for a second. And here's machine k minus 1 and some tasks scheduled on that. So we assume by contradiction there's some better algorithm which uses less machines, which uses only k minus 1 machines and can still execute all tasks without having them overlap. But our greedy algorithm, what we just described here, instead uses k machines, uses more machines. So let's look at what the first, why do we need k machines? Let's look at what the first task is that we scheduled on this machine. So here's task, let's call it I, that our greedy method had to schedule on machine k. So why did our greedy method schedule it on machine k? Well, our first step was to check, was there some machine for this task? And in doing so, we checked all of the other machines, and if there was one which was available, which didn't conflict with this task, then our greedy method would have scheduled it on that machine. The reason why our greedy method needed to create this new machine k in order to execute this task was because all of the other machines had some task that they were executing, which meant that they couldn't execute this task I. Meaning that this task conflicts with at least k minus 1 other tasks, one on each of the other machines that we've got. So that means that there's no non-conflicting schedule using k minus 1 machines, because we've got at least k tasks, all of which overlap with each other with this task. So that means that there isn't a better schedule. It's really not possible to use less machines than what our greedy method uses, which means our greedy method is optimal. We do use the least number of machines possible. Okay, what might not be immediately clear is why this runs in big O of n log n time. So we start off by going through each of the items that we have, so you should notice that the number of times we're going to go through this while loop is big O of n. We'll have n iterations, one for each task that we have. And we have to be careful how we accomplish these operations so that we do them most efficiently, because if we're not careful about how we implement this, then we're going to get something which runs in worse than n log n time. So we could do like we did kind of in the previous lecture. So if we want to remove the task that has the smallest start time, we could just sort them all in advance. So before we start going through all tasks, sort T by ascending start time, or descending start time, whichever you want to go with, so that just the first or the last one, that is already the task that has the smallest start time. That way we don't have to scan through each one, which means that one execution of this line will be linear time. And we're going to run this line n times, which means so far our total is big O of n. But now we have to figure out, how do we check efficiently if there's a machine that can handle this task? We want to avoid comparing this task to all of the other machines that we have, because in the worst case, we could have a lot of machines. Maybe all of our tasks conflict, in which case we have a machine for all of the tasks that we've gone through so far, which means comparing this task to all of the other machines we've got would be linear time. Just checking once to see, does this task conflict with all of them, checking each of the other machines individually. We could have n other machines. So we want to avoid comparing against all of the other machines. So instead, we're going to pick one particular machine to compare against. So let's say we've got, here's machine 1, machine 2, let's say we've got a few machines. Say machine, I don't know, Okay. And I'll just draw it this way. And we've got some tasks scheduled on each machine. Maybe some machines have a few tasks scheduled on them. And we've got a few of them. We're going to keep track of, for each machine, because for the task that we're scheduling next that we want to schedule, we don't have to compare this task to all of the other tasks on any particular machine. We just have to compare it to the last task. So for each machine, we're going to keep track of what the last task is, specifically what the end time of that last task is. Because since we're working in ascending order of start times, then that means if we get some task next and we compare its start time to the finish time of this next, of the machine that we want to schedule it on, if they overlap, so for example, let's say we want to schedule this task here. So it doesn't have a machine just yet. This is its start time, this is its end time. If the start time of this new task comes after the end time of the last task on one of these machines, then that means we could schedule this task on that machine. Whereas if this start time comes before the end time of the last task on some machine, then that means these tasks overlap and they conflict, meaning we wouldn't be able to schedule this task on this machine. So we only have to keep track of what this end time of the last task on a given machine is. So when we schedule a new task on a machine, we're going to update its end time appropriately, since we've got a new last task scheduled. But again, we want to avoid comparing this task to every single machine. So instead, we're going to keep track of which machine so far has the earliest last end time. So of all of these last task end times that we're keeping track of, we're going to figure out which one of them is earliest. Now, we can't sort them initially because, again, we could have n of them, and if we're calling that, we would have to sort it each time appropriately, which would be n log n time to just sort it once. So instead, we're going to maintain a heap, a min heap, of machines based on this end time. So we're going to maintain a minimum heap of all of the machines that we've created so far, and we're going to use the keys, use as keys the end time, the finish time of the last task that we've scheduled on that machine. So now, rather than comparing this new task that we want to add, this task I here, we want to schedule this on some machine if we can, rather than comparing it against all of them, we're going to take the minimum one, whichever machine has the earliest end time. Because if we find that this task conflicts with the last task scheduled on that machine that has the earliest end time, then that means that if they're conflicting, then this task will also conflict with the last task on all of the other machines. So we're only going to compare when we're checking to see, is there a machine for this task I that we're adding? The machine that we're going to check, rather than all of them, we're just going to check that machine that has the minimum end time, which means that in order to find what that is, we know that'll be the root of our heap. So to remove it would be log of whatever the size of our heap is. Now this is the number of machines that we have, but in the worst case we've got n machines, one for each task. And we're going to compare our task against that single machine. And the reason for that is because if that task doesn't conflict with this machine, then perfect, we've already got the machine that we need in order to schedule our task on. And in doing so, we change the end time of that machine, so we're going to add it back to our heap with that new value, which is also log end time. But if we find that this task conflicts with that very specific machine that has the earliest end time, then that means that this task will also conflict with all of the other machines that we have. So in that case, we know we have to create a new machine. We can add the machine that we checked against, add that back to our machine heap. But then we have to create a new machine, and on that new machine, we're going to set its end time to be the end time of the task I that we just scheduled on it. So this is what makes our running time n log n. N log n in order to sort tasks by ascending start time. Then we have a while loop, which iterates n times. We can then remove a task, just if we were to call this once, it's constant time. But the remaining part of this, checking which machine, figuring out which machine we should compare against, and then updating it appropriately or creating a new machine as necessary, this is log n time. And that logarithmic running time, just to execute this if statement once, that logarithmic running time comes from removing from our heap of machines, removing that machine that has the earliest end time, and then comparing our task against that machine to see if it can be scheduled on it. Okay, so our total runtime is big O of n log n. So let's see this in action. Let's go through an example next. So let's say we've got the following tasks, and they are already ordered by their start time, but note that we could be given tasks in any arbitrary order. And now our first step should be order them all by increasing start time. And I'm kind of giving away here that ultimately we'll need 3 machines, but we don't know that yet. So we start off with 0 machines, and we're going to add them as necessary. So our first step is here's our first task with the earliest start time. And we can break ties arbitrarily if they have the same start time. So we're going to schedule the task 1-4, and we need a machine in order to do that. So we've got 1 machine now so far, and we're only going to add them as necessary. So we've got this 1 machine. We've already scheduled the task which starts at 1 and ends at 4, and again these are fixed start and end times, so you can't change them or shift them to start or end at a different time. Now we schedule the task 1-3. So we're going to compare it against our machine. Our machine ends at 4. Now our start time for this task is earlier than the end time of our machine, which means it can't be scheduled on machine 1. We need another machine to execute it. So this is where machine 2 comes in. So now we've executed our first 2 tasks, and we maintain for them right now for machine 3 its end time is 3, and for machine 1 its end time is 4. So when we get to the next task, which starts at 2 and ends at 5, we're going to first check to see, will it fit on machine 2? We pick machine 2 because it's got an earlier end time. We're not even going to compare it to machine 1, because if this conflicts with machine 2, then it'll also conflict with machine 1, which is the case here. So we realize once we get to this task that we need our 3rd machine. And we say for that machine, okay, the last end time now is 5 for machine 3. Now when we get to the next task, 3-7, which starts at 3 and ends at 7, we're going to compare it to machine 2, because that's got the earliest start time. Note that this ends at 3, which means we can immediately start another task at 3. So we're going to schedule this task on machine 2. Now we update, its new end time is now 7. We go to schedule our next task, 4-7. We're going to compare this to the machine that has the smallest end time. So we've got our heap of machines, and machine 1 has the earliest end time. So we're going to check to see if it conflicts with this machine 1. If it doesn't, we're going to schedule it on that machine. If it does, then it conflicts with all the other machines. So we would schedule it on a new one. But it works out that we can schedule it on machine 1. And when we do so, we update machine 1's new end time is 7. So note that machine 1 and machine 2 have the same end time. So in our min heap, we would just break our tie arbitrarily. So now when we compare for the next task we want to execute, we would compare against machine 3 first, because this machine 3 only, because this machine has the earliest end time, and it doesn't conflict with this machine, so we can schedule that task on machine 3. Okay, lastly, we have the task which begins at 7 and ends at 8. We're going to compare it to, let's just say, machine 1 to break ties here. And it can be executed on machine 1, so we schedule it there. Okay, so we can solve this task scheduling problem in n log n time. And we did so using a greedy method. So we're always processing tasks based on the earliest start time. And scheduling it on a machine if it can be scheduled on a machine. If not, then we create a new machine for it.